Let's talk about eigenvalues and eigenvectors of matrices. Now, this is a formula you will see in books and on websites. A being the matrix, V, sometimes X is used to represent the eigenvector of the matrix, and lambda, the eigenvalue, right? Now, eigen is German for own. So, the eigenvector of a matrix is the matrix, the matrix's own vector, and the eigenvalue of the matrix is the matrix's own value. All right. Now, this formula represents the matrix times its eigenvector being the same thing as the value of the matrix times the eigenvector. So instead of using the whole matrix to multiply the eigenvector, you could just use the value of the matrix to multiply its eigenvector. All right. Now, here, if you consider, for example, A being the matrix, say the matrix has elements, and it's a 3 by 3 matrix, right? Say A, let me write them, A, B, C, D, E, F, G, H, I, right? And by the way, one of the first very valuable set of video lessons that I found was on Prime Newton. So, Prime Newton's channel, PRIMENEWTON, Prime Newton. There are many other very valuable channels that offer lessons on matrices, but that's one of the first that I saw that was very detailed. All right. So here now, A, B, C, D, E, F, G, H, I. That's our matrix times its eigenvector. Now, a vector as a matrix representing a vector is a column matrix. In this case, let's say we have our X, Y, Z to be our column matrix, is equal to, we're going to run out of space. Now let me just move these down a bit. Right. Now that is equal to lambda. Now lambda is not a matrix, it's a single number, times the eigenvector, the same eigenvector, X, Y, Z. Right. Now, what you have in the next step in analyzing it is that the matrix times its eigenvector minus the eigenvalue of the matrix times its eigenvector is equal to 0. All right. So what that is saying is that the matrix A, B, C, D, E, F, G, H, I, is I not T, multiplied by its eigenvector X, Y, Z minus the eigenvalue of the matrix multiplied by its eigenvector X, Y, Z is equal to 0, right? Now, here, if you should multiply these, you would get 2 column matrices. All right, you would have ax plus by plus cz, and you'd have dx plus cy plus fz, then you'd have gx plus hy plus iz being equal to lambda x, no, minus, I mean, not equal to, minus lambda x, lambda y, lambda z equals 0. So column matrix equal column matrix. And remember, when you multiply a matrix by a scalar, which is a number, you multiply each element by that number. Alright, good. Now, if you factor out the eigenvector, you will get x, y, z. Then you would have your a, b, c, d, e, f, g, h, I. All right, minus lambda equals 0. Now, at this point, you recognize something, right? And it was Prime Newton that I saw explain it. Why is it that you multiply lambda by I? Right? I saw in some notes they did not really have the matrices written out like this, but they had V. What they had was when you factor out V, you have V times A minus lambda I equals 0, right? But why do you multiply by I? All right. You have a matrix here. How can you have a matrix by a number? Minus a number. I know you can multiply a matrix by a number, but you cannot have a matrix plus or minus a single number. It must be matrix minus matrix. And it must be in the same order of the matrix. So you cannot have this. So in order for you to have matrix minus matrix, what you must do? Multiply lambda by the identity matrix. So let's move these things to the side to make space. All right. What you're going to have is lambda times the identity 3 by 3 matrix is 1 0 0 0 lambda 0. Why am I writing 0 1 0 0 0 1, right? Seem to be stepping ahead, multiplying by lambda already. Oh, this should not be a square bracket, it's a round bracket. Let me correct this here. Is really a round bracket. And then we have our square bracket after. Oh, the one disappeared, let me put it back. Right? So we have, this is what we have. The vector times, in bracket, matrix minus lambda I. Because I is the identity matrix. So, what we'll end up with is this now. x, y, z times our matrix A, B, C, D, E, F, G, H, I minus lambda 0, 0, because remember, lambda times 1 is 1 here, lambda times 0 is 0, lambda times 0 is 0. So remember, you're multiplying a matrix by a number, so we multiply each element of the matrix by that number. Lambda by 0 is 0, lambda by 1 is lambda, lambda by 0, 0, lambda by 0, 0, lambda by 0, 0, lambda by 1 is lambda. And all of this is equal to 0. Good. Now what is, alright, let's rewrite this. So using the notation, it's V times the matrix A minus, this is lambda times the identity matrix equals 0. Good. Now, the thing is, the next step says that this is supposed to be 0. The determinant of that matrix is supposed to be 0. Why? Alright. Suppose the determinant of that matrix is not 0. You could have vector times A minus lambda I equals 0. Now, it means that if you make this equal 0, make some space there, and you can find the inverse of this matrix, then you could say A minus lambda I inverse is equal to, just multiply both sides by the inverse, A minus lambda I inverse. Good. A minus lambda I times its inverse is the identity matrix. So the vector, the eigenvector times I is 0 times the inverse of the identity matrix, but 0 times anything is 0. So what that would mean is that our vector x, y, z multiplied by 1, 0, 0, 0, 1, 0, 0, 0, 1 is equal to 0, 0, 0, 0, 0, 0, 0, 0, 0. So we cannot multiply them like this. We have to switch around. So we have our 1, 0, 0, 0, 0, 1. I mean 0, 1, 0, 0, 0, 1 multiplied by our eigenvector x, y, z being equal to 0, 0, 0, 0, 0, 0, 0, 0, 0. So when we multiply, we run out of scrolling space, we can't scroll down anymore. Let's continue in this area here. 1 by x is x plus 0y plus 0z, but you know these will amount to 0, so it's just x, right? So we get that vector here. Oh, let's rewrite. So it's of x, then 1, 0 by x is 0, 1 times y is y, and 0 by z plus 0. So we have y alone. So 0 by x plus 0 by y plus 1 by z. So we have z is equal to, alright, 0, I represented it as a 3 by 3 matrix, but also could be represented as a column matrix. 0, 0, 0. These should really be column matrices. So let me rewrite them as column matrices. So that would mean x equals 0, y equals 0, z equals 0. Ah, easy. All of them are 0. But no, you can't do that. So you should have a situation where you cannot find the inverse of this. Alright? So you should not be able to find the inverse of this. Now, what type of matrix you cannot find the inverse of? Is a singular matrix, where the singular matrix is one where the determinant is 0. So the determinant of this must be 0. Alright? Alright, so we look at, I had previously posted video with examples, but I'm going to post more examples where you'll find the eigenvalue and eigenvectors of actual matrices.